Okay, now we can start. So, hello everyone. I am Edi Tribaskoro. Good evening and also good morning in Ottawa. Welcome again to the Combinatoric Today series. This is the 11th edition in this year of 2023. Today, we are delighted to have Professor Vida Dujmovic as our speaker. She's a university research chair and professor of computer science at the University of Ottawa, Canada. Her main research areas are graph theory, in particular geometric and structural, and she has published over 80 journal papers. She's a recipient of the Earlier Researcher Award by the Ontario government and Clincy Award for Excellence in Research by the University of Ottawa. She's an invited speaker at the 2024 European Congress of Mathematicians. Today, Professor Vida will give a lecture on the proof of the clustered Hadwiger Conjecture and will be chaired by Professor Joko Supriyanto. I think this is new results regarding and related to the famous Hadwiger's conjecture, and we are very, very grateful and happy to listen some this exciting progress.
Thank you so much.
In this occasion, allow me to thanks to the Faculty of Mathematics and Natural Sciences, ITB Bandung, and the Center of the Research Collaboration on Graph Theory and Combinatorics for the continuous support to this program. And now, before we start, let us to take a photo. So I would like to request Pak Joko to guide us to take a photo and also to share this lecture.
Thank you.
Okay, thank you, Betty. So, hello everybody. Please turn off your camera in order to take a picture of us. Farhan and other things not yet turn on the camera. We are still waiting for some other participant to turn on the camera. Palton Faisal and Wei Liu, maybe David Hui. Also Andrico. Can you turn on your camera, please?
Okay.
Okay, ini sebagian
Maximum.
memang ini, ya. Okay. Okay, I will count. 3, 2, 1. Okay. Once again. Sekarang Ferry ya?
Ya.
3, 2, 1.
Okay.
Okay. It's all okay. Thank you. Thank you very much. So, okay, I will continue to share our discussion. So let me first introduce the curriculum vitae of Professor of our today's speaker, Professor Vida Dujmovic. So I'm so sorry. There is
Very good.
Okay. Yeah. I will share my screen. Yeah. Can you see it?
Yeah.
Okay.
Yes.
Okay.
Oh. Oh my God.
Okay.
Belum. One more. The first page.
Yeah. Okay. Yeah. Okay. I will introduce Professor Vida, the curriculum fit of our today's speaker, Professor Vida Dujmovic. Professor Vida obtained his PhD in computer science at McGill University, Montreal, Canada, on 2004, and Master of Science, again in the same faculty and same university in 2000, and also he finished his honors Bachelor of Engineering from University of Zagreb, Croatia in 1996. And he's now a full professor in the School of Electrical Engineering and Computer Science at the University of Ottawa, Ontario, from May 2023. And before it, for about 5 years, he is also an associate professor in the same university and same faculty. And from September 2013 until April 2018, he's also an assistant professor, still in the same university. And right after he finished his PhD, up to August 2013, she has several positions, academic positions, in several universities, I think, including postdoctoral fellow, research associate, and adjunct research professor, and also assistant professor. And Professor Vida also obtained many awards and honors. Among them are as follows. From 2023 up to 2028, he's a university research chair in the structural and algorithmic graph theory. And in 2023, he obtained George S. Glinsky Award for Excellence in Research from the Faculty of Engineering, University of Ottawa. 5 years before, she also obtained an award, a Best Paper Award in 26th International Symposium on Graph Drawing and Network Visualization. And when she was much younger than now, he has also obtained the so-called the Early Research Award from the Ministry of Research and Innovation, Ontario. So I just list a very view of award and honors she obtained actually. Regarding the editorial board, she served as an associate editor for a very high-level journal, namely SIAM Journal of Discrete Mathematics from January 2020 up to present. And before it, she's also an associate editor of the Journal of Computational Geometry. And regarding the scientific article, her profile, as I mentioned by Scopus, is like this. If before Pak said that Vida has published over 80 scientific articles, actually due to Scopus, she has published over 100 scientific articles with age index 22. And now, as Pak mentioned before, she will talk about one of the big problems, I think, in the area of graph theory, the so-called proof of the clustered Hadwiger conjecture. So without further ado, let's invite her to give a lecture. So Vida, please, the time is yours.
Thank you so much. Thank you. Okay, let me share the screen first. I am trying to, maybe haven't opened it yet. Let's see where the file is. Just a moment, I'm looking for that file. Okay. Do you see the slides?
Yes, yes.
Okay, very good. All right, let me open. I'm going to go to full screen. Is it full screen now?
Not yet. This is different.
But it's not the the slide of your talk, I think.
Oh, okay. Let me start.
Mhm.
I saw that there were two files, and it looks like my ticket. One of them looked like my ticket, and then I thought I changed it.
Right,
Try
yeah.
again. Sorry. All right, let's try that again. Slides. I had it prepared, and then I don't know where it disappeared. But this is going to take a second. All right, so. All right, so now it should appear. All right, it should be correct now.
Great, right.
Okay, now you see the slides and not my flight.
Yeah.
Okay. All right, let me just try to not have it automatically. Should I start?
Yes.
Yes.
Yes, please.
I'm trying to stop it. Sometimes it goes on by its own, the flipping of the pages. All right, I think I managed to. No, I didn't. Okay. I don't understand this. Just a moment. Okay. Thank you so much for inviting me. It's a pleasure to give a talk. I have never been in that part of the world, so it's really nice to be even remotely with you in Indonesia. So I will talk about, as already introduced, I will talk about a version of Hadwiger conjecture, so who clustered Hadwiger's conjecture, which is relatively new, especially compared to the original conjecture. I will tell you about it. But before I do, let me introduce the colleagues that I obtained these results with. Louis Esper, he is in University of Grenoble. Pat Morin, he is also here in Ottawa, but in the other university, Carleton University. And David Wood, he's in Australia, in Monash University in Melbourne. So this is, as already introduced, the result is really new. So we obtained it this spring. Basically in January and February, Pat and I were both on sabbatical, visiting Louis Esper in Grenoble. So this is our office. That was in January. This is beautiful city of Grenoble. It's beautiful even in January and February. And we started working on this problem. And by the end of it, we solved it, which was quite unexpected. So it was really nice sabbatical. It was a 3-month sabbatical there. So let me introduce a problem by starting with one of the oldest problems in graph theory, or at least in graph coloring. In 1852, British, I believe he was British. Hopefully I'm not saying something incorrect. At least he was a student in Britain. Francis Guthrie, he was a student of botany and mathematics and was studying at University College London. And he noticed that a map, regions of the map can be colored, or at least that he was always succeeding in coloring them with 4 colors, such that no 2 adjacent regions get the same color. So here's an example of that coloring of the regions in UK with 4 colored. And he asked if all the, so that we are talking about 1852, he asked if all planar graphs can be, or planar maps can be colored with 4 colors. So in a graph theoretic setting, actually, the problem problem is the same as coloring of the graphs. So to see where the graph comes from, all one has to do, if you want to color regions like here of Australia, all one has to do is put a vertex in each region and then connect two regions by an edge if the regions share a boundary, a non-trivial boundary. So here, this would be a graph representing regions in Australia. And then what one wants to do is the color vertices of a graph such that no two adjacent vertices, so no two vertices that share an edge, get the same color. So that here in example, we see that this graph is colored with 3 colors. And because we have 3 pairwise adjacent vertices, actually three colors are necessary. Okay, so basically the question from those 1850s was whether every planar graph, and planar graphs, if you create graphs like this by starting with a map on a plane or on the sphere and put vertices in regions and connect them by edges if they share non-trivial boundary, it turns out that the resulting graph doesn't have edge crossings. So rather it can be drawn such that we don't introduce crossing of edges like in this picture. So basically the question that Guthrie asked, the equivalent question, is whether every planar graph can be colored with 4 colors. And this was a very famous problem, still is a very famous problem, but it was solved about 100 years after the original problem was asked. It was solved by Appel and Haken in 1977 with the help of computers, a simpler proof, but still with the help of computers. But the number of cases that the computer had to solve was much smaller, was obtained in 1997 by Robertson, Sanders, Seymour, and Thomas. So by now, the problem is considered well established and solved, although it's still a very difficult problem. There is still, this one would like to find a simple proof of 4-color theorem, but that's not what I will talk about today. Okay, so let me first introduce what a minor of a graph is, because that is an object. Those are the types of graph that we will be studying in this talk. So we say that the graph H, so think of H as being a smaller graph, is a minor of graph G, so think of G as being a bigger graph. If this graph H, the smaller one, can be obtained from G by deleting, what is allowed is to delete edge, delete a vertex, but also contract an edge, right? Because contraction is less obvious what it does. So I have it here in the picture. So this orange edge here, if you want to contract it, is like you take 2 endpoints and you glue them together. Okay, so you would get a graph like this. You may have 2 parallel edges, but remember, in a minor operation, one is allowed to delete an edge. So here we contracted this orange edge, and if there would be parallel edge, we deleted it. Okay, so again, to obtain a minor, you're allowed to delete an edge, you're allowed to delete a vertex, and you're allowed to contract an edge. Okay, so planar graphs are minor closed, meaning if you start with a planar graph and then you delete an edge, so you start with a drawing with no crossings, you delete an edge, it still has no crossing. If you delete a vertex, it still has no crossing. If you take an edge and kind of put these vertices closer and closer together, it's possible to do that without introducing crossing. So in other words, planar graphs are so-called minor closed family. You stay in the family when you perform these operations. Okay, so here's one example. On the right-hand side, we have a bigger graph, graph G. So if you look at this red or pink subgraph, I can contract all of these edges and get this pink vertex here. Orange subgraph, if I contract, I get this orange vertex here. So you can see that if I contract pink and orange and green and blue subgraphs, I actually get a complete graph on K vertices. These gray edges and vertices hanging are deleted. Okay, so this is just an example. So here we see that K4 complete graph. So we started with this planar graph, but through the operations of contractions and deletion, so through the minor operations, we can get complete graph on K vertices. We can get K4. So K4 is a minor of a planar graph. Okay, so planar graphs can have K4 as a minor. However, it is well known that planar graph cannot have a complete graph on 5 vertices as a minor. Okay, so K5 first cannot be drawn without edge crossings, and it has been known that for I would say probably, I forgot, Wagner, maybe 100 years, that planar graphs don't have K5 as a minor. So in the way we were, so we can now look at what is known about the graph that exclude a certain small minors. What is known about their number of colors that are enough to color them. Okay, so let's go backtrack now, even a simpler thing, and see what was known before. So first of all, if you have a graph and exclude, and you say a graph family doesn't have a single vertex as a minor, but then the graph is empty graph. You don't even have a one vertex, so you can color it with 0 colors. If you exclude a complete graph on 2 vertices as a minor, like in my second line, so that's, you're saying I'm excluding an edge as a minor, but that means that the graph doesn't have even a single edge. So its graph is a set of isolated vertices, so you can just use one color. Okay, so therefore the chromatic number of such graph is 1. If you exclude K3, K3 is a complete graph on 3 vertices, then that means your graph class doesn't have cycles. So in other words, this is trees and forest, and it's well known that they can be colored with 2 colors. Okay. Series parallel graphs are graphs that exclude complete graph on 4 vertices as a minor, and they are known already from 40s that they can be colored with 3 colors with a simple greedy coloring. Such graphs have always, you can find a vertex of degrees at most 3. That means that you can remove that vertex of a degree at most 3, color the smaller graph inductively, and then when you put back that vertex of degree 3, if you want to color with 4 colors, well, 1 color is available, so you just use a 4th color. So this simple greedy strategy in these graphs that exclude K4 as a minor gives you 3 colors. Then a planar graph, thanks to the 4-color theorem, the result was generalized, and that's not so difficult, to the result that all graphs that exclude K5, so complete graph on 5 vertices, that includes planar graphs themselves, they can be colored with 4 colors. So it's like a generalization of 4-color theorem. And finally, for the last thing we know about excluding complete graph as a minor, how many colors you can color a graph with, is that graphs that exclude K6 as a minor. And in this case, we don't even have a very good idea of what these graphs look like. We don't have, in a sense that we don't have a very clean structure theorem like we do for K5 minor free graphs. So for K6, these are already very complicated graphs, a very complicated proof by Robertson and Seymour and Thomas showed that these graphs can be colored with 5 colors. Okay, why am I showing you this list? Because if you look at this list, it looks like that if a graph excludes K3, you need 2 colors, K4, 3 colors, K5, 4 colors. So it looks like it's a natural conjecture to conjecture that if every graph family that excludes KH, where H is now any constant, as a minor, is H-1 colorable. That such graphs you need one less. If you exclude KH minor, that you are H-1 colorable. So this was conjectured by Hadwigers in 1943. By the way, notice that in 1943, four-color theorem, the results for K5 and the result for K6 was not known. Four-color theorem was proved in 70s. So at the time when Hadwigers conjectured this, these last two lines in my table were not known. But this conjecture, we are very far from proving this conjecture. And I'll give you some indication of that. And I don't know if anybody is even ready to say, to firmly believe that this is true or not true, the conjecture. So we see that it's true for H up to 6. But let me tell you what is known so far. What is known, what was known in 1984, the best result was H times, that you can color such graph with H times log of H, so square root of log of H. So that bound is significant in the following reason. What they proved, Kostochka and Thomasson, what they proved is that actually something stronger. They proved that every graph that if you're looking at a family of graphs that exclude KH as a minor, they proved that every such graph has a minimum degree at most this. So it has a vertex that has at most this many neighbors, but that means that greedy strategy works to obtain the coloring. So you find the vertex of this degree, you remove it, you color the rest of the graph. When you put the vertex back in, there is always one unused color, and you use the unused color for the new vertex. So the greedy coloring, because this is a bound on the minimum degree, you know that you have a vertex with at most that many neighbors, greedy coloring works. However, this bound on the minimum degree is tight. So the minimum degree bound cannot give us better result. So we were stuck on this for almost 40 years. There was no progress because, so the best bound was based on the minimum degree strategy, greedy strategy. Finally, there was a big breakthrough by Noring, Song, and Postel, and that was in, I'm trying to see the year because my window is, it doesn't matter. I can't see the year, but it was a couple of years ago, maybe 5 years ago. It was first time the result, so this exponent on the log was reduced. So finally they broke the minimum degree bound, and they reduced the exponent to 1/4. There has been more progress in the meantime, and currently the best bound is H times log H, which is due to my colleagues Postel, who is in Waterloo, and Michel Delcourt, who is in Toronto Metropolitan University. Okay, so as you can see, we don't even have a linear bound. So not only that it's not known, this is super strong, is the number of colors exactly H-1. And by the way, notice that H-1 is necessary because you can have a complete graph on H-. If you're excluding KH, it means that you can still have KH-1 and complete graph on H-1 versus needs H-1 colors. Okay, so we are very far from H-1. In fact, what we don't have a linear bound in H. That would be a huge breakthrough if one can prove a linear bound on H. Okay, so this is, at this point, researchers often start to consider variations of the problem where you relax some conditions. So here's one condition that has been studied in the last decade, which you relax the condition that the vertices that are adjacent, that they have to have distinct colors. You're going to allow some of them to have You're going to allow some of them to have the same color. Okay, so here's what I mean by that. Let me describe the definition. We are still looking for coloring, let's say with K colors, or in my drawing here, you want to color the graph, let's say with 4 colors. But instead of saying that no two vertices are adjacent, what you allow is that if you look at each color class, so for example, let's look at this pink color class. If you look at the graph only on those pink vertices, so imagine the rest of all the other vertices are deleted. So you look at only on the pink graph, then the connected components of the pink graph have constant size. Or in this example, so we are talking about K coloring of the graph, where each connected component, we call these monochromatic components, the components where all the vertices have the same color, where they have a constant size. So this here would be example of 4 coloring, where each connected component, so let's look at the red connected component, has at most 4 vertices. Okay, so the green one has at most 4 vertices. In fact, it has at most 3 vertices. The blue color class has at most 4 vertices. And finally, the orange color class has at most 3 vertices. We call this coloring. So this would be a 4 coloring with clustering C. So the size of the largest monochromatic component is what we call clustering, size of your clustering. So in this case, the largest monochromatic component has 4 vertices. So this is 4 coloring with clustering 4. Notice that this is a generalization of classical coloring, because if you allow clusters of size at most 1, then you get back the classical coloring. That means that if you look at any single color class, no two vertices are adjacent in that color class. Therefore, clusters, you have just a set of isolated vertices, so you get a clustering 1. So each connected component has size 1. So generalized version, not generalized, Hadwiger's conjecture in this setting would be, can we prove that every KH minor free graph can be colored with H-1 colors, such that the clustering is a constant? It depends only on H. Okay, so let's look at an example. So again, let me make sure that we all understand the definition. A K coloring with clustering C is simply coloring of the vertices of a graph with one of K colors, such that each monochromatic component, so the connected component where all the vertices have the same color, has at most C vertices. So a 4-color theorem is the same as saying that every planar graph can be colored with 4 colors and clustering 1. Okay, so the cluster size is at most 1. Okay, and as I already mentioned, this is a difficult problem. I mean, it still is a difficult proof that planar graphs are 4 colorable with clustering 1. If you allow clustering 2 for planar graph, then actually we have a simple proof from 86. It's about 1 page long. There is a small mistake in this proof, but it's not difficult to fix it. So there is a simple proof that planar graphs can be colored with 4 colors and clustering 2, meaning if you look at each color class, the connected components in the color class are either isolated vertices or just an edge, or 2 vertices with an edge between them. Okay, so what about now that we allow this relaxation of coloring, is it possible, the natural question would be, okay, but maybe now planar graphs can be colored with 3 colors and constant size clustering, okay? But actually that turns out to not be true. So the clustered chromatic number of planar graphs is not 3. And there is a very simple example to show you that. So let's look at that. The graph looks like this. So you have this thing here is just a path. These are paths. imagine it's a long path, and then you have first of all, let's just look at what's inside of one triangle. First of all, you have a triangle, and then inside of a triangle you have a long path, and then these two of the vertices are dominating that path, like this white vertex and this red vertex. They're adjacent, they're both connected to everything on the path. So that's what's inside of one triangle. And then we repeat that graph many times, adjacent to this red vertex. Okay, so that's a planar graph. You can draw it without crossing, and this dot, dot, dot here indicates that you have many copies. So you're trying to say, I'm going to color this graph with 3 colors such that monochromatic components have components of size at most C. Somebody gave you this constant C. And I'm going to take here many copies, much more than C, of these triangular graphs. Okay, so now this red vertex, it's connected to everything. So it has to receive some color. So let's say it's red. So now let's look at these other, in each of these triangle, we can look at these colors that are adjacent to these vertices that are adjacent to everything inside of the triangle. So the other vertex. If you have many copies of these triangles, that means that at least one of them cannot be red. If all of these are red, then all of a sudden you will have more than C red neighbors, and you break the clustering rule. So you're getting clustering bigger than C. So in at least one of the triangle, this neighbor that is also adjacent to a long path, it does not have the same color as the red vertex. So we end up in this situation here, where we have a green vertex and red vertex, both adjacent to a very long path. But only constant number of vertices on this path can be red. Otherwise, only C number of vertices on this path can be red, because otherwise you get a connected component with more than C neighbors. The same for the green vertex. But that means if you take a very long path and you add the constant number of vertices somewhere in that very long path, there is still a very long path that is not colored left. But for that, you need 2 colors, because otherwise you cannot break the path into small components. You're going to have a connected path that has more than C vertices. So that shows you, this simple example shows you that you need 4 colors, that planar graphs need 4 colors. No matter what constant you give it, you won't be able to get a coloring with 3 colors and clustering C. So the clustered chromatic number of planar graph remains 4. So what is known about this is what we call clustered chromatic number, is simply for a class of graph is a minimum K, so minimum number of colors, such that exists some absolute constant C, such that every graph in that class can be colored with 4 colors and clustering at most C. Okay, so we just learned that planar graphs have clustered chromatic number 4. In fact, they have clustered chromatic number 4 with clustering 1. And in the early result, one of the biggest breakthroughs so far was that Dvorak and Norin proved this for all graphs embeddable on the surface. Okay, so all graphs of constant genus, they have clustered chromatic number 4. So what that means is that, for example, complete graph on 7 vertices can be drawn on a torus. So graph on genus 2, and K7 needs 7 colors. Complete graph on 7 vertices. So for the classical coloring, you need 7 colors. But on the surface now, if you allow, on higher surfaces, if you allow cluster coloring, all of a sudden, all of them, for a fixed genus, all of them can be colored with 4 colors, where now the size of your clusters depends on the genus. It's still a constant. So if genus is a constant, then the size of a clustering is a constant. And this bound is best possible simply based on the planar graphs. And this I'm going to skip. So let's go back to what we wanted to prove, is that we wanted to prove a clustered variant of Hadwiger's conjecture. which is that KH minus free graphs. The KH minor free graphs can be colored with H minus 1 colors. It turns out that H minus 1 is best possible, even for KH minor free graphs. And it's basically that same example that I showed you for planar graphs. That graph excludes K4 as a minor, and then that graph excludes K4 as a minor. So if you just, and it needs 4 colors, and if you want to get a more general example, KH as a minor, you would just add 1 extra vertex connected to everybody and repeat the whole example and so on. I don't want to go into that, but H minus 1 is best possible even in this clustered variant. You cannot break H minus 1, as we have seen for planar graph, where 5 minus 1, so 4, that they exclude K5 minor free graphs, so 4 is not possible. Sorry, 3 is not, H minus 2 is not possible. H minus 1 is best possible. So here's a history of this result. So going back, so first linear bound, so we are talking about going back about 15 years. First linear bound is obtained by in 2007. So at least we learned that unlike classical Hadwiger conjecture, we at least now know that linear bound is possible. In particular, it was 31/2, the first result. Then there was a series of papers in the following decade that reduced that bound age. Finally, in 2019, Liu and Wood prove a bound of at most H, so 1 away from conjectured bound. This proof actually is very complicated. It's in a series of 2 papers with altogether maybe 120 pages, and it relies on one very, very difficult 60-page lemma. So I think that our proof is much simpler, although they did prove something a little bit stronger than we proved. Our proof is not short, but I think hopefully it's much simpler. I'm going to try to give you an idea how we showed it, and plus we showed a tight bound. We actually showed the H minus 1 bound. Okay. So now the result is that, so we proved this clustered Hadwiger conjecture, namely that every KH minor free graphs is H minus 1 colorable with clustering at most f of H, depends. So if H is a constant, then f of H is some constant, some absolute constant. Okay. So, oh, by the way, I should mention that in 2017, this result was announced by Dvorak and Norin. Remember, they are the ones who proved that all the graphs on the surfaces, all the bounded genus graphs, can be colored with 4 colors. So in the paper at the end, they proved, they announced that in the follow-up paper, they will prove H minus 1 bound. But to our knowledge, that result has never been written. I heard recently that they are writing the problem, writing that result. I would be very excited to read it because, in fact, they proved something stronger. They proved a so-called choosability version of coloring choosability version of this problem. So their proof would have to be very different from ours because our proof would not give a choosability. We do operations that absolutely are not compatible with choosability. So it would be exciting to see these results nevertheless. Okay, so let me try to give you just a kind of global picture of how we prove this result. Okay, so we used various tools. First of all, we had to use graph minor structure theorem by Robertson and Seymour because that's the only tool that tells us what do these graphs look like? What do these graphs that exclude KH as a minor? We better know something about what these graphs looks like if we are about to make any programs. Then we use some results on known results on tree-width. Typically, I'm not going to define tree-width. If you're unfamiliar with tree-width, think of graphs that have constant tree-width as graphs that are kind of similar to trees. So they're much simpler, the general graph. We understand them well. We have many solutions. For many problems, we already have solutions for graphs that have constant tree, that are tree-like. Then we used our recently discovered tools. In 2019, we discovered this tool called graph product structure theory. That was one of the key tools that we used. And then we also used something called island method by Dvorak and Nori, then Esper and Oum, but I'm not gonna go into that. But first, let's look like, before we can attack this problem, what do these graphs that exclude KH as a minor, what do they look like? And the famous theorem by Robertson and Seymour tells us, so tool number one tells us, what do these graphs look like? How do you obtain a graph like that? So what they showed us, or what they taught, basically they proved this in a series of 20 papers in 80s, that family of graphs that exclude KH as a minor, each graph as a family can be obtained, this is called structure theorem. It can be obtained in a following way. So you start with, in my picture, you see this, you start with disjoint graphs. Okay, so you have unbounded number of them. I mean, you're trying to make some graph on n vertices. So you have these, and you're going to make them from these smaller graphs, G1, G2, G3, and so on. So first of all, you need to know what these smaller graphs look like. For now, think of these graphs G1, G2, G3 as being bounded genus, being graphs that can be embedded on the surface, but not quite. There's more things, so it's a bit of a lie. But let me tell you what you do then. So you start with these graphs G1, G2, G3, and then to an operation that you're allowed to do is you find a complete graph in one graph, let's say G1, you find the complete graph on the same vertices. In this example, we have K5. So you find a clique on the same side in G1 and G2. You identify the vertices of these cliques, maybe remove some edges in just in this clique. And that's one operation you're allowed to do. It's called clique sum. Okay, so what Robertson and Seymour showed is that graphs that exclude KH minor can be obtained by disjoint graphs that are so-called almost embeddable on the surface, that you can obtain them by doing these clique sums. Okay, so you can start with these and then you start gluing these graphs on the clique until you finally obtain your graph. So every graph that excludes KH minor can be obtained like that. Okay, so here it is, repeated again. So G, which is KH minor free, can be obtained by clique sums of G1, G2, G3, where these graphs are almost embeddable. Okay, so imagine, so the first thing, if you want to color the whole graph with at most H-1 colors, then you better be able to color each piece, each of these individual graphs with H-1 colors. So you better be able to do that, okay? So a standard strategy in coloring would be, okay, you first color this graph G1 with H-1 colors, and then you find this clique on which you have to glue. It's already pre-colored. So, and then now you try to add to it G2, and you try to extend that coloring that was already there on 5 of the vertices. So you kind of want to prove it inductively. So let's see what would go wrong. So imagine you already colored G1, and now you want to glue G2, 4 of its vertices in this example already colored. Now you want to extend the coloring to the piece that you just added. So in order for that to work, let's just look at this picture. So you colored this G prime, some first graph, you colored it, and there is some here small cluster of green. So you have a connected component of size C, constant size, that is green. So when you add this new, when you glue this new graph, what you want is that the neighbors in the new graph of the pre-colored vertices, you don't want to color them the same colors as this clique that is already colored. For example, you don't, if you have a vertex like this, it's adjacent to green guys, although we allow some vertices to have the adjacent vertices to have the same color, you really would like to avoid that. And the reason is that if this cluster was size C, by giving this one here color C, you are now enlarging the green cluster. Remember, we wanted constant size. And even if just one neighbor is green, you are in trouble, because we can repeatedly, remember these species in graph minor structure theorem, they all can be added onto the same cliques. We don't have a restriction of how many of these species can be added to the same clique. And if you're adding many of them to the same clique and at least one green vertex is added in each, you are enlarging this grid connected component and you are in trouble. So what you really want to do is that when you're adding the new piece, this clique is already colored, you want neighbors on that clique to actually not receive any of the colors that are already there. But here lies a big, big problem that on all these years that we were stuck on, which is that Robertson and Seymour structure theorem, it tells us that this clique that we are gluing on, it tells us that this clique is of constant size depending on age. But it's not like it's at most h minus 1. All we know that is at most f of h, where actually this age can be exponential. So this clique here on which we're gluing, although it's a constant, it's huge. And all we are trying to say, okay, you're gluing on a huge clique, you're using h minus 1 colors, but now you don't want any of the neighbors to have h minus 1 colors. That is really a big problem. I mean, that is simply not going to work. So the gluing on these big cliques was a tremendous stumbling block for us. Okay, so that was the problem with this kind of, if you try to attack this problem. Okay, but so there are two things. First of all, if you think of Robertson and Seymour structure theorem, you have to color each piece. That's number one. And then how you do this gluing, right? So you have to be able to color each almost embeddable graph, each of these individual graphs, and then how do you glue them together? Okay, so let me show you how to color these individual pieces. By the way, here's one way to think of graph minor's structure theorem. You can think of it as a tree, where each node of this tree is one of those pieces of, graph G1, G2, G3, and then an edge in that tree is showing you should do a clique sum of G1 and G2. And then this edge here is telling me next you can do clique sum on G2 and G4, right? So you have a kind of a tree-like structure representing these clique sums on the pieces of Robertson and Seymour structure. Okay, so we want to color, how do you color one of these pieces with h minus 1 colors? So let's look at what, so let me finally explain what do these pieces look like, these disjoint graphs. We better be able to do each one of them. So here's what we learned from Robertson and Seymour structure theorem. What do these graphs look like? So first, imagine that you are on some surface of fixed genus, and you first start with a graph that have a crossing free drawing on that surface, okay? So if that was all, then we would be very lucky, because that would be bounded genus graphs, and we know we can do them with 4 colors, right? But unfortunately, that's not all. These pieces, by the way, called almost embeddable graphs, they're called almost embeddable because they don't look like that, right? They are not embeddable on the surface. Instead, Robertson and Seymour told us, in addition to having this embedding in a surface, there is a constant number of faces, that the little yellow things in my drawing, where you have some mess, which is not without crossing anymore. So there's a constant number of faces where crossings are allowed, But inside of these spaces, this crossing, this graph that is inside of this constant number of faces, it's kind of well understood. These are so-called bounded path with graphs. We typically know what to do with them. But even that is not all. Then there's a constant number of vertices that don't live in the surface. You can think of them as being above the surface. There's constant number of vertices called minor apices that connect to, that are allowed to connect to these messy faces, to the vertices in these yellow messy faces, the constant number of these faces. So there is a certain number of those. They're called minor apices because they're only allowed to connect to these messy faces. They're not allowed to connect here in the rest of the surface. But then they are really bad guys, okay? There's constant number of them. Why am I saying they're really bad? They can connect to anything, right? Anything on the surface or in this. By the way, what I call these messy faces, they're called vortices in the Robertson Seymour language. So these major apices, they can connect to everything. They can connect to vertices in vortices, and they can connect to any vertex on the surface. And you can imagine here why that is a problem. Let's backtrack and forget major apices for now and vortices. If you look at the rest of the graph, because there is only constant number of these vortices, if you look at the rest of the graphs on the surface, the thing that I color green, this is a bounded genus graph. The rest of it is bounded genus. So remember, we already have a result that you can color bounded genus graph with 4 colors. Okay, so maybe you have, if you're just ignoring the big problem, maybe you can color the rest of the graph on the surface with 4 colors, but then here comes this apex vertex, and if you give it one of these colors, so let's say we're looking here at this pink color or red color, pink, I guess. If one of these major apices, you give the same color, and it can be adjacent to anything on the surface, now all of a sudden you glue all of these red vertices that were not even adjacent, they are now neighbors of one red vertex, and you have a huge cluster. You create a huge red cluster with these apex vertices. So these apex vertices are really problematic, these major apex vertices. Okay, so but still, how did we do this? You see, this is an example of creating a huge pink cluster by adding this major apices. So they spoil everything. They're really problematic. But for now, let's see, what if you don't have this major, what do we do if we don't have these major apices? If the graph looks like everything I told you, surface, constant number of vortices, and apices adjacent to vortices, well, then we can use our product structure theorem that we discovered in 2019 that tells us that such graphs have the following property. So let's look at a picture. All such graphs, what you can do is you can imagine that you partition vertices in layers. Think of it as a breadth-first search layering. Okay, so what does that mean? Here's layer 1, and here's layer 2. All the edges in a layering are either within a single layer or between 2 consecutive layers. Okay, so think of it, breadth-first search has that property. If you do breadth-first search, you look at the layering, edges are only within a layer or between 2 consecutive layers. Okay. So here's layer 1, here's layer 2, 3, 4, 5, 6, and so on. So what we showed in a product structure theorem is that such graphs can be partitioned into paths, into vertical paths. So paths that cross each layer at most once. So it looks something like this. Here's or I'm not showing you all the partition. I'm just showing you some of the partitions. Here's a green path, a red path, blue path. So basically, you can partition all the vertices into these paths such that if you contract each path, like in this picture, I'm showing you paths are contracted. That picture shows you contract each path. You end up with that bounded tree with graph. Remember the graphs that I told you we understand well. the graphs that are tree-like. Okay, so you start with this almost embeddable graph without messy big apex vertices. What we can show is that you can contract these vertical paths, and the resulting graph has a constant tree width, so it's tree-like, and the graph is still a minor of the original graph. All we did is a contraction. So we end up with a graph that has bounded tree width and this KH minor free one, and still exclude KH as a minor. So in that case, we already know, remember I mentioned already that these bounded tree width graphs, we often know the result. Okay, so we know already that this graph, once you do a contraction in this nice graph, we can color it with H-2 colors. So we even save one color. This is kind of a bit, there's lots of technical conditions here. This is kind of a lie, but it's okay, lie. But so this is, we can color this graph with H-2 colors. And remember, we are trying to do H-1. Okay. So this smaller graph, after contraction, we can color with H-2 colors. That means we have one color saved. Okay. So now, remember, we have to color this graph when we uncontract it. So we saved one color, and now I uncontract. But now when I uncontract, you see, I may have long paths, meaning I may have that uncontracted vertex may have many vertices, and they are, let's say, are you looking like here, they're all red. So I have to break this red component. So this can create a long red connected component, which is not allowed. Remember, monochromatic components have to have constant size. But now I can use that color that we spared to break these long paths. So here's a picture that just shows that. I'm not going to go into it much. So you have these long components, the red one. Let's say this purple is your saved color. You have long red paths, long yellow paths, green paths, but you save this purple color. And because you use breadth first search, so there are edges only between consecutive layers and one layer, you can break this path. You first use, let's say, purple color in layer 7 to break a red path. So now there's only a component of size 6. Then you skip one layer, and then you break a yellow path, then you skip a layer, break a green path, and you alternate. In that way, you can break all the long paths and have a constant size coloring. So you have H-1 coloring with the constant size components. Okay, but that only works if we don't imagine now one of those major apex vertices. So this thing here is a coloring of almost embeddable graph without those major apex vertices. Imagine now they come and, you know, they're adjacent to all of this, so they glue this again, these long paths into one component. Okay, so they are still a problem, but at least we know how to color this thing on a surface without these major apices. Okay, so all right, so now let's say we know how to do pieces of the graph structure theorem. What allowed us to overcome these major apex vertices is a version of structure theorem that is actually due to Dvorak and Thomas, which says that number of these really bad guys, the number of minor, the apex vertices that can connect only to vortices, there can be f of h of them. There can be a lot of them, but they were not a big problem for us. The bad ones, there's only H-5 of them. So that allowed us to overcome that problem with major apex vertices. Okay, so I'm not going to go into why. So now we know how to do each piece. I know it doesn't look like I'm close to an end, but now I'm getting close to the end of the talk. We know how to do the pieces, And now we want to start doing click sums. Okay, the problem that I mentioned at the beginning. Okay, so how do you now, so imagine I now colored using my strategy, I now colored this G1, and now I have to glue on a click G2. I glue it on the click such that the neighbors of the click don't get any of the colors that I used on the click. Okay, so, and remember the problem was that these, that we are gluing on a very big click sums. Okay, so how did we overcome that? How do you do click sums now that we know how to do pieces? So this Dvorak and Thomas version of structure theorem, not only does it tell us that the number of these bad apex vertices, that there's not too many of them, right? We know much better about it. It's at most h-2, so the number of bad apex vertices is at most h-2, but their version of structure theorem tells us something even more useful that helps us, not more, as useful, that helps us do these big click sums. It tells us that if your click sum is big, if you are doing gluing or two graph on a very big f of h, where h is, can be, f of h can be exponential in h, if you're doing gluing in the structure theorem on the big click sums, then those two clicks have to be on the top of the graph, in that mess, on those vortices. They cannot be in that nice surface part that I was showing you at the beginning, the one that I colored and says, oh, we can even do it with 4 colors. So the big click sums involve only the top of the graph, the messy part with vortices. So in order to not be gluing at all on the big click sums, what we do is we perform those click sums before we even color, before starting to color anything. We do these click sums. So if you think of this graph minor structure theorem, you can say this piece and this piece, they need to be glued on a big click sum. I'm going to do it immediately. Okay, I'm not going to color this and then try to add that one. So the thick edges in my picture show you some of these pieces are glued on a big click sum, and the thin one tell you, oh, these two are glued on a small click sum that I'm going to do by induction. Okay, so let's look at that. So what this picture says, if you have a big click sum, the click sums that are big involve only the top of the graph. There cannot be vertex in the surface part that is involved. If there is a vertex on the surface part, then your click sum is small, is at most h-2. And remember, we have h-1 colors. So now this is much better. We can hope to do something when we're doing click sums because it's going to be only on h-2 vertices rather than f of h, which is here. Okay, so this is my last slide about the proof strategy. Instead of having a structure theorem where each of these pieces is almost embeddable graph, we are working with a structure theorem where each piece is pre-glued. You think of these pieces, you imagine each piece is like a sheet of paper. Each graph is drawn on a sheet of paper, but you only glue them on the top. So each piece is now almost embeddable graphs that are glued on the top if it was big click sums. And otherwise, the rest is glued on the small click sum if the surface is involved. So in that case, so now you have to color one of these glued pieces already. So you take of these graphs, you perform all the big click sums, and now because it's big click sums are only performed at the top, you can still apply our product structure theorem to contract them and get a bounded tree with graph. So we can still apply the same strategies. I don't want to go into details, but the same strategy that we can apply for one piece, we can now apply to these pieces that are glued together. We contract them, we get bounded tree with graph, color them with h-2 colors, uncontract them, and then break the colors. So that would color one of these blobs But now we can perform clique sums. We can handle it because the remaining clique sums are of size at most h minus 2. Okay, so that's all about the proof. I hope it wasn't too many details. I was trying to keep it on high level. I would just like to mention for the end a result that was in the key thing for solve is the version that I presented you. That version is talking about this partition into parts and contraction of the parts, but a simpler version to digest. Our main result from 2019 says that every planar graph and every bounded genus graph is a subgraph of some graph H, where H has that constant 3 with. And remember, those are the graphs for which we have solutions for many problems. So it's a subgraph of a bounded genus graph, in fact, genus at most 8, and a path. Okay, so you have a strong product. So often, if you, first of all, path, we already know how to solve everything on paths. And then many problems already have good solutions on bounded 3 with graphs. So if you're looking to solve something on planar graph or bounded genus graph, maybe there's already a result on paths and bounded 3 with results. So then you can use the structure theorem to just extract the result on planar graphs. And that's what we managed to do. In the last 3 years, we solved a number of long-standing problems using the structure theorem. So if you are going to take away anything from this talk, this is a list of problems that were solved since 2019. Many of them were like 20, 30 years old. So this is not what I was talking about, but just to say that if you would take something from this talk, it would be that possibly the usefulness of this product structure theorem for planar graphs and bounded genus graph, and maybe if there's a problem you're working on and in some planar graphs, maybe the tool would be helpful for you too. And by the way, the product structure has been extended to some other graph families, but it's time for me to stop. I hope I wasn't over time by much. Thank you so much.
Okay.
Thank you.
Okay. Vida, thank you for a very interesting talk, although it's not too easy for me to catch up. A very high level talk about proof of outstanding conjecture in graph theory. So we were entering the discussion session. Paidi will give us a video of an art performance, I think.
Yes. Okay.
Yeah, please, Paidi.
Okay. Thank you. So before we begin with the discussion, now I would like to present some performance, music performance. This is performed by actually the group of our colleagues, Dr. Rinovia Simajunza. So the choir will sing a song about this is Moon River. Probably you know the song, yeah? Okay.
I think I do. Okay.
Okay, let me share my screen. Okay. Just a moment. Just a moment. Just a moment. Yeah.
River, style someday. Oh, dream maker, your heart breaker, wherever you're going, I'm going your way. Oh, drifters off to see the world. There's such a lot of world to see. We're after the same rainbow's end, waiting round the bend, from the very bright Huckleberry moon, river and me.
Okay. Back
That's
to
great. Are they all professors?
only one.
Only one. Okay.
Yeah.
Dr. Renufia. Yeah. The others, I think, different profession. Singer, at least
Wonderful.
singers.
Yeah.
Really.
But but Rino, two actually, Pak Edi. Two, yeah.
Oh, okay.
Oh,
two.
the one
The other
from
is-
Carlton, right?
From Cal, yeah.
Yeah.
Okay, everybody. Now let's. Okay, I will invite all of you to give a question or comment, please, if there are any.
Okay,
You
probably.
can- Pak Edi?
Yeah,
Okay,
yeah,
please,
okay.
Pak Edi.
Yeah. So first of all, this is quite a higher lectures. Yeah, you know, a high level lecture. So I'm not familiar in this area, but I knew several things, like the things that you present in the proof of planar graph, which are not tricolorable with a bonded clustering.
Yeah.
That was very nice. Nice
Yeah.
ideas. Yeah,
that
I
is
like
really
I
good.
like it to see the counter example and so on. Yeah.
Yes.
And
yes.
yes, and the second one, the clustering ideas. So okay, so in the clustering, it's not necessarily sub-click, yeah, or click, yeah.
No. It
So
does.
can
it's not
be
necessary.
any
And
graph.
it can be any graph as long as it's
Any graph.
constant size.
Only in the size you bound it. Yeah.
Yes,
the
all we
size.
care about the bounded size, not what it looks like. No.
Okay. And you use a lot of nice ingredients, yeah, like the
Yeah,
trim.
this one we were lucky. We were lucky. I really didn't think.
You haven't mentioned about the island.
I did not mention by the island. That's
Yeah.
because, you know, during this presentation, I'm trying the paper is still about 60, 70 pages long. I was
Oh.
trying to give a high level so some of the things that I told you, remember when I say I'm lying here, right? When I said that every graph that looks like a tree and doesn't have a K-H minor, you can do with H minus 2 colors, kind of a lie. We had to actually use serious techniques there for this lie to become true. We
You
were
must
lucky to use this. We
several
really used I don't know how this happened. In fact, we were going after, remember how I said that there was already, we didn't even think we can prove H minus 1.
Oh, okay.
So what we really wanted to do is find a simple proof of H. And David Wood and Chung Hung Lee, they had a proof of H that I found so complicated, I couldn't follow it. I really tried to understand. They have this lemma that is 60 pages long. I couldn't understand it, but we really were looking for simple a proof
Simple
of
proof, yeah.
that result.
Uh-huh.
And we originally thought that they had H+1, not H. And we were trying to understand, have a simpler proof of that. And at the end, we obtained simple proof of H. And but then we realized, oh my God, they also had H, because there was a third paper where they had H. And we were so disappointed. So sometimes, also save their students in the university, sometimes this happens to everybody. You realize, oh my God, this result that I have, somebody already have it, and you're so disappointed. But it made us, we never would have probably, we would stop, right? We have an H, we beat their result, and it's simple proof, we would have stopped. But then we realized, oh my God, H was already known. There was nothing left but to go after the main thing. And that's where we added even more techniques, more hammering, and it works. Sometimes it doesn't, most of the times it doesn't, but sometimes every now and then we succeed. But very often it's like that. You prove something, you realize, oh my God, this was done, or it's wrong, or I don't know, happens there. So many lucky things happened in this. For this
so
result.
you think that you can make it simpler, the proof, not 81 pages?
Yeah, so we try. Yeah, so I am not sure, but what we at least try to do when we were writing the paper, what we at least try to do is give a simple, before this, we for example have a super simple bound of H+4. So if somebody wants to get kind of the main idea, what is it that this allowed this to work? How did we use product structure theorem? We first give a simple proof that of the bound H+4, not H-1. So we were trying to and at some point, then the reader can decide, okay, I can stop. I think I've seen at least the main idea, understand this tool, so I can maybe use it in something else that I'm trying to show myself. So we try to break it into, let's prove, do a simple proof of H+4, simple proof of H+1, and then go after these more complex things where we have to do islands and technical parts.
And do you think, is there any generalization of the clustering ideas? Probably come up with some new ideas.
That's a good question. Mostly the way these things are strengthened typically in the community is that instead of doing classical coloring, that you look at choosability, meaning that every vertex, you don't get to, if you want to use, let's say, 4 colors. If you want to ask, is the graph 4 colorable? That means you get to choose, you're going to use only 4 colors, 1, 2, 3, 4. In a list version of coloring, you don't get to choose the colors. Each vertex has its own list.
Yeah.
Listing one, you're allowed to use color 107.2. So each vertex has a list of, and in my case, it would be each vertex has a list of H-1 colors. It seems like, why would that be more difficult? But it actually is much more difficult. They are bipartite graphs. So the graphs that you, in classical colorings, you can use, you can do it with 2 colors, but that they need unbounded number of colors if in the list version. So the list version is much more difficult. And in fact, it is known that the classical Hadwiger conjecture is not true for list coloring. So it's not true that KH-free graphs have a coloring with H-1 colors where the lists are given to you of size H-1. So the next thing would be to prove this clustered version, but the list coloring. And as I said, Zdenek Dvorak and Sergei Norin, who usually obtain absolutely spectacular results, they say that they have that proof. So that would be the next thing.
Okay. Thank you very much.
Thank you so much.
Nice.
Thank you for inviting me. Thank you. Okay. Have a good night.
Okay, so maybe one last question.
Oh,
No,
Oh, sorry, I thought
finished,
you were
not
saying
finished
the
yet.
goodbye. I
I'm so sorry,
misunderstood.
Vida. Okay, so if no, so I will go back to Paidi. Maybe Paidi will give a last statement for you, Vida.
Thank you.
Okay. Okay. So thanks again to Professor Vida Dujmovic for very nice and exciting lectures and also discussion. And on behalf of the Faculty of Mathematics and Natural Sciences, ITB, we would like to present you, Professor Vida Dujmovic's A certificates of this
Thank you.
of these lectures.
Thank
I will
you.
show you the certificates and also some small token from us. Okay, let me present you the certificates. Let me see. Oh no, just a moment. Oh, here we are. Okay, yes. So this is the certificate, and actually we also have these things.
Oh, great. Thank you.
So I will send
Email
you
me that?
this to document. Yeah.
Okay, great. I love it. Thank you.
Okay. So thanks again, Vida, and hopefully next time you can visit us here to Bandung. Yeah.
I would love that. I have never been anywhere in Asia, so
Oh yeah.
hopefully,
Okay.
yeah, I would love that. So hopefully next time it's going to be in person.
Okay, will be wonderful. Okay,
Thanks.
so thanks, Professor Vida Dujmovic, and also thanks
Thank you all.
everyone
Thank
here.
you, Professor
Thank you
Vasco
all.
Esperianto. Thank you.
Yes.
Yeah.
Have a
And
good
see you
night.
Thank you,
again.
Vida.
Yeah, good night, and good morning over there.
Yeah.
And see you
Okay.
probably next year. We will continue our program, our webinar. So this is actually a series, yeah,
Yes, I
Combinatorial
know.
series, yeah. So we will continue next year.
Wonderful. Okay.
Okay.
Thank you so
So
much.
bye-bye
Thank
from
Bye.
Thank
Bye.
you.
Okay, thank you,
Bye.
Vida.
Thank you.
Saya stop recording.